Uh, okay, so our third talk is about scaling distribution-oblivious systems with low-touch distribution. The speaker is Nikos Vasilakis.
Thank you. So in the previous two talks, we heard a lot about the benefits of distributed systems. I'll repeat two sentences. So distributed systems have significant benefits over their centralized counterparts. The ability, for example, to scale out computation, the ability to tolerate failures, the ability to store more data, all tons of interesting benefits. Reaping these benefits, however, is difficult today, primarily because the way we develop for distributed systems is significantly different from how we develop for non-distributed systems. Whereas anybody can write a Python or Ruby or Bash script to compute on a single machine. Here I have a simple word count example. Scaling out to multiple computers requires either learning new programming languages, new programming models, hooking up tons of different frameworks to compute on a few machines. Now, this disparity is even wider. This disparity between distributed and centralized computing is even wider with the use in centralized computing of third-party packages, third-party modules, or libraries. I'll be using these terms interchangeably, which make it really easy for anybody to just hook a few scripts, a few packages together with a little bit of glue code, and voila, they have an application up and running, which is great, until the point, of course, that the application hits a scalability, a bottleneck, and it needs to scale out to multiple computers. At that point, the developer has to do a couple of things. The first is identifying the bottleneck, which, because most of the code base is foreign to developers, they will have to really dive into their third-party dependency chain and understand where the bottleneck is. This is really tricky. And then after they have identified the bottleneck, they need to rewrite it to exploit distribution. This is even more difficult than the first step, of course, because of all the problems I described earlier. The fact that you have to write in new programming languages and all these problems. Worst of all, this process, these two steps, have to be repeated for every new bottleneck discovered. To give you an example here, I have a very simple application where the developer imports a couple of modules, the file system module and the Markdown compiler, which is a third-party module, and they use it to compile a Markdown file to HTML. Now, this Markdown compiler is a third-party module whose parse function takes 1 second per file, which is okay. If you have to just compile a couple of files, this is okay. But if we have files arriving every half a second or so, this will quickly saturate the system. It will not only affect the Markdown module, the Markdown compilation, which is, of course, will start behaving badly, but it will also affect other parts of the application that fight for the same set of resources. Okay? Now, the developer has, as I said, they have a few tools they can use to understand the problem. They can capture and replay traces. They can use some statistical profiling, generate flame graphs, and then they will have to analyze and map these results to the module, to the dependency chain, to understand what is it that takes so much time. What is it? What is the bottleneck exactly? And the second part that I described earlier is really to write a distributed version of the Markdown compiler, which is, of course, much more difficult. They have to express this program in a few possibly frameworks. It might not fit in the paradigm of a single distributed framework. They will need to either or a distributed programming language. They should arrange for communication between the distributed part of the computation and the centralized part of the computation. They have to orchestrate jobs, make sure that everything starts and stops at the same time, and then they will have to schedule calls accordingly. So based on which client has the least load. So they will also need to write parts of a scheduler. All of this is really, really difficult today. Okay, makes sense? So the question we ask and answer in this paper is whether we could do a little bit better. And the approach that we're proposing is what we call light touch distribution. That the idea is that as long as the developer has sprinkled the application with a few high-level semantic annotations about the resulting distribution, our framework should be able to automatically detect and scale out bottleneck components. Okay? This is the key idea. And I'm going to break down this idea into three separate high-level ideas. If you are to remember a single slide from this talk, it should be this one. The first part is a set of automated runtime transformations that wrap modules and their environment and introduce profiling collection at the boundaries of individual modules. Okay, this is the first part. Of course, because these wrappers have visibility only at the module boundary, they need to send periodic statistics to a somewhat centralized coordinator that will rank modules and decide which of these modules have higher need, which ones should scale out. Okay. The second part is a set of parameterizable runtime transformations that launch, when they detect load, they replicate modules. And of course, they need to replace local calls with RPC calls that will choose the right replica and send arguments there, run the computation there, and fetch results back to the consumer module. Okay? There are tons of technical details, such regarding forwarding calls, converting local references to distributed references, propagating state mutations and collections that I will not have time to cover, but are in the paper, and I will be here to answer technical questions. Now, the third part is that because of fundamental inescapable trade-offs in distributed systems that we keep discovering, such as the CAP theorem, FLP, all sorts of fundamental trade-offs, we need to give developers the ability to tune the resulting semantics of the distributed application. One example is ordering. So if you have a module that requires or expects order calls, we need to maintain this invariant in the distributed version of the system, right? We need to know about that. So the third part of the system is this idea of high-level distribution recipes that selectively retrofit single runtime semantics to the distributed version. Okay. So going back to our example, the first thing we do, we import our Ignis module that will change how the require statements work. These import statements, instead of just reaching the file system and loading code, they will transform the return value of these modules to add wrappers that I will discuss in a second. And of course, the first thing they detect that the Markdown compiler takes too much time, or there's too much of a load. So they will scale out the Markdown compiler and schedule calls to the replicas. Now, how do these wrappers work that I just described? This is a key idea in this work, all these transformations. So I'm going to show you a couple of transformations abstractly. So the key idea is when we get the return value of an object, of a module, which is an object, we have to traverse this object, okay, and replace certain, for example, function calls with other function calls that do something else. In the case of monitor, for example, that we'll have to add a prologue and an epilogue that will capture profiling statistics. Okay. The second part, a similar transformation that I described earlier, is converting these local calls to remote procedure calls. So we'll have to send a message, first of all, pick a replica, send a call there, ship the arguments, get the results back. Okay? This is a key idea. Now, how do we know when to scale out? This is mostly, I think, this is mostly a simple idea where for every call arriving to the system, Ignis checks the servicing time on the current processor, on the current module, and if it's going to be higher, like it depends on how many calls are waiting to be serviced, and the average latency, of course. If it's higher than the round trip latency of sending the call to a remote replica and getting the results back, of course, it's going to schedule the call to a remote replica. Okay. Now, how do we know anything about the average servicing latency? With this profiling, the prologue and an epilogue that I just described, that captures profiling information at the beginning of the call and end of the end of a call. Then we take a weighted windowed average across the latest n calls to adapt on the workload. So if if it changes, we have to know about that. Now there is a question of, so many modules might want to scale out. So for many modules locally, this heuristic might make sense to scale out. But if we have a limited amount of resources, how do we decide which one to scale out? This is where the centralized coordinator comes in, that I just discussed a little bit earlier, which ranks these modules based on periodic statistics that it gets from the module boundaries, and then decides which one of these modules it makes most sense to scale out. Okay? Now, there are a couple of details that I didn't describe. In particular, I showed you, for example, how to convert the local calls to remote procedure calls. I showed you how to when to decide when to scale out. But there are a few cases when a local name in the replica has to be resolved either to a global value or a value or needs to be propagated back to the original application. Okay. The example that I had in the example that I showed you earlier, for example, console log shouldn't show results in the replica, of course, because it should show results back at the original output stream. Okay. So to do this, we have to replace such names with Ignis augmented values. For this, there are of course names that resolve to packages, to modules. So for example, we might want to replace the file system module with a distributed file system, and Ignis comes with a distributed version of the standard library. Or names that come from the programming language, even if you don't import something, they should resolve to the semantically correct version. For example, console log, as I said earlier, should output results back at the original module. And here the idea is to shadow variables in a way that allows Ignis to interject a step in the variable resolution process, so that in the local module sees only Ignis augmented values. Okay, instead of seeing the original value of console.log, we run another set of transformations that should change these values, these functions, for example. I'm going to show you how this works in a little bit of technical details. So the first thing we do is intercept the require statement that I showed you earlier, the markdown for the markdown compiler. Then remember, since this is an import statement, we're about to import the source code from the file system. Okay, so everything I'm showing you on the right is still source code. It's just a string. So the first thing we do, we run a simple source-to-source transformation that encloses this code in a closure and redefine global variables as function local ones. So this, if this makes sense, it's only to so that the module does not see the global, the original values, but it sees only Ignis augmented values. Okay. And of course, we'll need to we assign these values from a modified context. We'll just build together. So here, a context is a mapping from names to values, and we provide all the required names with the base transformations that I described earlier a few slides ago. So that that convert function local calls to remote procedure calls and all these details. Okay. And the final thing is, of course, evaluating the module from source code to actual an object in memory, and pass the context, call the function with this modified context. Okay, I'm sorry. There are tons of technical details, as I said, that I didn't have time to cover, as well as an extended evaluation in the paper. I want to give you a couple of highlights that I think are interesting. So we evaluated a few applications. Before I go into the applications we evaluated, I want to emphasize that there is, in some sense, a spectrum of difficulty, of manual effort you need to put in order to distribute an application. Some applications are really difficult. They have thousands of modules, hundreds of thousands of modules, and they have hundreds of thousands of lines of code. this is where Ignis would shine, right? This is where it really shines, because you just pass a few lines of code, the annotations that I described earlier, and Ignis will take care of automatically detecting bottlenecks and scaling out bottleneck components. Okay, this works nicely. The big question, I think the most interesting case, this idea came from a reviewer actually, is how would Ignis work in the other end of the spectrum, where distribution is really trivial? Like, would it actually be able to provide any benefits? And here we use this tutorial blog service, which is on the order of 50 lines of code, and it was really easy to plug in something like Redis on MongoDB. It's a few lines of code. I think 11. The delta is 11 lines of code, and of course you need a little bit of setup, but it's really easy. Like the model is really what is a perfect fit for these systems. And even there, Ignis gave a significant speed up with really an order of magnitude lower changes than these systems. This was a surprise. Okay, closing. There are several, I think, interesting avenues for further research, because Ignis and the ideas here make a few assumptions, simplifying assumptions. So, for example, we assume pervasive use of modules. What could you do if you don't have this pervasive use of modules? We have to infer boundaries, for example. Or we don't do full fault tolerance. Okay, the standard library we're providing is fault tolerant, but not everything is fault tolerant in Ignis. It doesn't result in a distributed version of the system that is fault tolerant. Okay, so I think there are tons of interesting research directions. This is a first step towards automatically distributing applications, and I can discuss more about other interesting challenges and opportunities for further research offline if people are interested. So I showed you that light touch distribution allows reaping distribution benefits for programs that were not explicitly designed to exploit distribution with minimal developer effort. That's a key idea. Thank you very much.
Thanks for the talk. That was good.
Thank you.
Nice. What happens with consistency? Do you have any consistency problems?
Yeah, there is a set of consistency recipes. I didn't have time to touch a lot on the recipes. These distribution recipes that affect the transformations and the semantics of the resulting distribution. We have, in the implementation, we have two consistency levels, but I think I think this design shows that if you care about more consistency levels, which of course you care in distributed systems, you can encode these as recipes and provide the associated transformation. And I think it would also aid formal understanding of, because if you've understood the formal semantics of the centralized computation, the centralized program, and you only provide a recipe, which is a name for a set of transformations, you only care about verifying the transformation at that point, and the result should be much easier than verifying a distributed program from scratch. And we can talk more about that.
That actually covered my question.
Oh, great.
To be honest, it was also my question, but I have a quick follow-up, which is, do you have any notion of the numbers when you use full consistency redistribution? Is the 27 times speed up the fully consistent case, or the oblivious parallelism case? In
that case, so it depends. There are cases, I mean, and I think CRD is one. There are cases, let's say that you can get away without full eager consistency guarantees, and in that case it was mostly a pure function that was taking CPU time.
So what is the kind of speed up we can expect if we need to use the full consistency recipe?
It really depends on the application and the workload. It's not necessarily an Ignis. It's not related so much to the transformations that I described. I mean, they will just hook things up and make sure you propagate side effects and a bunch of other things. It's a question about what your application is, and it's a much higher level question, I think, than the low level techniques mechanism that I showed here.
Thank our speaker again.
Thank you.